Hello, everyone. In this video, we're going to talk about the MathStat Prelim from August 2021, and we're going to talk about problem 1. Now, in this problem, we're given a sequence of random variables xn, and they are defined to be binomial with parameters n and p equals 1/2. I'm not sure if we're going to need that 1/2 or not. I'm going to try to do as much as I can in this problem with a generic p. And we're given that yn is 1 plus 1 over the square root of n to the xn times 1 minus 1 over the square root of n to the n minus the xn. And we have a couple of questions to answer here. So in part A, we want the expected value of yn. And it tells us what this is. It actually says show that the expected value of yn is, and it gives you something. But let's just see if we even need that. Is that a hint, or can we find this expectation directly? Okay, so this yn is a function of the xn. And so we can use the law of the unconscious statistician. I mean, you don't have to quote that. It's supposed to be so natural and unconscious for you that you just do it. But we've got the expected value of yn is the expected value of that whole big expression with the xn's in it. And because the xn has a binomial distribution with parameters n and p, I want to multiply this by the binomial PMF or PDF and sum over all possible values. So those possible values are going to be x going from 0 to n. And then the expression here that we're taking the expectation of, I get 1 plus 1 over square root of n to the x, and 1 minus 1 over the square root of n to the n minus x. And then still on the same line, but I've run out of room here, I'm going to multiply by the PDF for x, which is n choose x, p to the x, 1 minus p to the n minus x. Or if you went ahead and plugged in p equals 1/2, that's okay too. So this actually doesn't look so bad. I mean, it looks horrible actually, but there's like these exponent x and there's exponent n minus x. So I think the first thing I would do here is try to combine things. So I've got the sum as x goes from 0 to n of n choose x, and then p 1 plus 1 over the square root of n raised to the x, 1 minus p 1 minus 1 over the square root of n raised to the n minus x. So that's not bad. That looks like a couple of things to me. It looks like we can get away with a summing without summing kind of problem by comparing this to a binomial PDF, or we can just apply the binomial theorem. So remember, the binomial theorem says that the sum as, say, k goes from 0 to n of n choose k, a to the k, b to the n minus k, this is a plus b to the n. And so I've got, instead of k's, I've got x's, but we've got an a part over here and a b part over here. And so the expected value of yn is the sum that you're seeing sort of in the middle of the screen right now. And according to the binomial theorem, this is a plus b to the n. And that a, again, is p 1 plus 1 over the square root of m. And we're going to add b. b is 1 minus p, 1 minus 1 over the square root of n. And we get it all to the nth power. I don't know if we can cancel this down without, yeah, I don't think we can. I think I'm going to need the fact that p is 1/2. So let's go ahead and plug that in. I thought maybe I could get the result regardless of what p was. So when I plug it in, I get a 1/2 here and also a 1/2 here. And so let me pull that 1/2 all the way out front. Then I get a 1 plus 1 over the square root of n plus 1 minus 1 over the square root of n. And that is all to the nth power. So we get 1/2. And then in here, we just get 2. And that is to the nth power. So we get 1 to the nth power. And we get 1. Which is what we wanted. Not bad. Okay, let's talk about part B. In part B, we're looking at a new sequence of random variables Zn defined to be the log of the Yn's, and we're asked to find what this converges in distribution to. And we're given an odd limit here, which I assume is going to be useful. And we're given a couple of hints. So one of them is not to use CDFs, which honestly would be my first idea, because convergence in distribution is shown by convergence of CDFs. So I'd probably look at the CDF for this. But as soon as you start doing that, because X is discrete, it's going to be pretty ugly. CDFs for discrete random variables are not the nicest things. And also the hint tells us not to do that, and also not to use moment generating functions, which, by the way, you should know going into the prelim that if you want to show convergence in distribution, you need to show convergence of CDFs, and that's equivalent to showing convergence of moment generating functions, or you should do something else if a hint tells you to do something else. So here it says to rewrite this in the form Yn is some AXN plus Bn, and use the fact that Xn has the same distribution as the sum of n Bernoulli random variables. Okay, so I've got the Yn, and just as a reminder, now the Zn is the log of the Yn. So I'm going to take the log of this, and I've got a product which will turn into a sum, and I've got exponents that will come down in front. So I've got Xn log 1 plus 1 over the square root of n plus n minus Xn times the log of 1 minus 1 over the square root of n. And given the hint that I want to get into this form, let's combine this Xn and this Xn piece and write this as Xn times the log 1 plus 1 over the square root of n minus the log of 1 minus 1 over the square root of n times Xn. So those two logs came from this, and then there's the negative over here, and that made this. And what's left? I've got the remaining term, which is this n times this log. So n times the log of 1 minus 1 over the square root of n. So we're in the form of an ax plus b, as the hint told us to be in the form of. We can simplify a little bit. I don't know if you'd call it simpler, but if we do what I think you want to do with this, and that's make one log of a quotient, we're going to see the log, well, we're going to see almost the given limit hint. So let's do that. This is the log of 1 plus 1 over the square root of n over 1 minus 1 over the square root of n, Xn, and the rest. Okay, what to do now? I don't have the square root of n up here that I would like to see if I want to use the given hint. But we are given that the Xn is the sum of Bernoullis. It's the sum of n Bernoullis with parameter p. And convergence and distribution for a sum is making me think central limit theorem. And so the Xn is asymptotically normal because it's a sum of Bernoullis, and the mean for Xn is whatever the actual mean is. And that's the mean for the binomial, which is n times p, and the variance is the variance of Xn, which is np 1 minus p. So what I do know about Xn is that, so this is going to imply that Xn minus np over the square root of np 1 minus p is converging in distribution to a normal 0, 1. But that is not really what I have up here. So let's kind of force it to look that way. What if I take the, let me make this a little smaller. If I take the thing at the top of the screen right now, and I write this as the log of 1 plus 1 over the square root of n over 1 minus 1 over the square root of n. What if I replace that xn with xn minus np over the square root of np 1 minus p? I'm not done. I have to also write this term, but I want to stop and think about what I've just done. It looks like if I need to make this equal to the line at the top. So I'm going to need to multiply by, oops, wrong color. I'm going to need to multiply by the square root of np, 1 minus p. And I'm going to need to add on a term, which basically came from subtracting this times this. And I don't want to forget about the original second term, which is up here. So let's see if we can collect all of this and get this right. This is going to be plus n times the log of 1 minus 1 over the square root of n plus np over, nope, not over, just np times the log of 1 plus 1 over the square root. Yes, that's right. Square root of n over 1 minus 1 over the square root of n. Well, this looks like an awesome nightmare, but I'm thinking Slutsky's theorem. I know that this goes in distribution to a normal 0, 1. The stuff that it's multiplied by are a bunch of constants. So let's look at this and this. That is going to be the square root of np, 1 minus p, times the log of 1 plus 1 over the square root of n over 1 minus 1 over the square root of n. And that is really close to the given limit. In fact, if I pull out the square root of p, 1 minus p, then what I'm left with is exactly the thing that we were given the limit for. And so I know that this whole thing goes to, I know that this goes to 2, and this just stays where it is. So this whole thing goes to 2 times the square root of p, 1 minus p, which maybe we should use the fact that p is 1/2. This is 2 square root of 1/2 times 1/2. So this whole thing is 1. And that's not convergence in distribution. That's just convergence of a sequence of numbers. So that tells me, looking back at this mess towards the top of the screen, this is going to a normal 0, 1, and I'm multiplying by stuff that is going to 1. And that tells me that this entire term here is going to a normal 0, 1 by Slutsky's theorem. So to finish this, we just need to figure out what this goes to. And you notice there's no random variables there. So if we can get the constant here, then we will be done. This answer is going to be some sort of normal distribution, and probably not 0, 1, but something else 1, because the second term here is shifting the distribution and therefore changing the mean, but not the variance. To summarize, we're looking at Zn. This is the log of xn. This is some an xn minus np over the square root of np, 1 minus p, plus this other term that looks like this. So I'm going to call this bn. And so I guess I'm not using the an and bn as in the hint anymore, because it was an xn plus bn, but I expanded this into something that I could use the central limit theorem on. So this an is not the same thing as this an anymore. And if you add or subtract a constant from a normal, it's still normal and it's not going to affect the variance. So we already have that this thing is approaching in distribution a normal 0, 1. And if we can figure out what this is approaching as a number, then the whole thing will be approaching in distribution a normal 0 plus the number and then 1. In other words, normal number 1. Okay, so again, the number is the limit of this Bn that's sitting here. This does not look like much fun, but it also does not look like much statistics. And when you're taking the prelims, the graders are looking, yes, for a whole package, but if it's in particular, I can say I've been on a couple of different subject prelim committees, and the stats people usually are concerned. I mean, they're concerned whether or not you can do computation for sure, but it's more important that you know the probability and statistics. So I think that we have the bulk of the problem and we'll attempt this limit. And if it goes poorly, you should just write, kind of this, like what you're trying to do and what you're trying to see, because the grading committee for the prelim always appreciates a plan and a cool head and common sense. I am hoping that if we undo this log thing that we put together, that maybe this will simplify. So I'm going to rewrite this as n log 1 minus 1 over the square root of n plus np. P is, of course, 1/2. You can be using that all along. Log 1 plus 1 over the square root of n minus np log 1 minus 1 over the square root of n. Let's put the p in. So p is 1/2, and this term looks like this term. And actually, if you subtract those two terms, you have n over 2 log 1 minus 1 over the square root of n. And then here, because p is 1/2, you get n over 2 log 1 plus 1 over the square root of n. Okay, so we need to take this limit and we are done. If you just start looking at it term by term, as n goes to infinity, this is going to go to infinity, and this is going to go to the log of 1, which is 0. So you might be thinking to do a L'Hopital's rule on each term, but I think, and you would, I think, get there, but that would take a long time. I think we can put these logs back together. So we've got a sum, and that would be a log of a product. This is n over 2 log of 1 minus 1 over the square root of n, 1 plus 1 over the square root of n. And if you multiply that stuff out, you get log of 1 minus 1 over n. Yet again, I want to use L'Hopital's rule and go for it, but there's something cute going on here. I can write this as 1/2 log of 1 minus 1 over n to the n. Or I could have brought the 2 up as well. But what I'm seeing inside here in this limit is e to the -1. So maybe you brought the 1/2 up in the exponent, and you would see e to the -1/2, and you'd be taking the log of that. And in any event, this turns out to be, well, I'm going to write it the way I've been doing it, 1/2 log of e to the -1, which is 1/2 -1, so -1/2. And that was that b term on the A, well, not the hint, but let me scroll back. That was the b term in here. This is the thing we want to look at convergence and distribution for. We wrote it as a constant that goes to 1 times a random variable that by the central limit theorem goes to a normal 0, 1. And now the Bn is going to -1/2. And so we can put this all together and say that Zn, which is the log of Yn, is converging in distribution to a normal with mean -1/2 and variance 1. And I would quote Slutsky's theorem just for putting all of those limits in the sum and multiplication together. And yeah, we're done. So I will see you in the next one.